Welcome back to the deep dive. Today we're digging into something maybe a bit unexpected. It's the Tamiya foam motor cover.
Yeah, that little black sleeve. Yeah.
Exactly. The one you get with those high performance brushed motors, like the dirt tuned part 53929 or the super stock BZ, the 53930. And you look at it and honestly, you probably just toss it aside, right? Like it's packaging foam or something trivial.
Or maybe just a dust cover in the box.
Yeah. But I want you to really think for a second. How much actual engineering could go into just a simple piece of foam?
Well, our sources, they paint a totally different picture. Our mission today really is to show you why this cover isn't just an accessory. It's actually an integral part of the motor system.
Really?
Tamiya basically custom engineered it to solve a really tricky problem, a paradox that came up right when brush motors were hitting their peak performance, especially for off-road.
A paradox. Okay, I'm intrigued.
Yeah, we need to uncover why it was needed, how it actually works, and why you barely see them anymore. It's about the clash between speed, heat, and survival in the dirt.
All right, let's get into it. Section 1. The vulnerable engine, the 540 class brushed motor.
So before the foam makes sense, we got to talk about the motor it protects.
The standard 540 brushed motor. Pretty simple, right? Steel can, armature inside spinning.
Right, copper windings, the end bell, and crucially, the brushes and commutator. Carbon brushes rubbing on copper segments, classic stuff.
But that simplicity has a weak spot, doesn't it? Especially when you push for performance.
Absolutely. The core issue is heat. You get heat from the electricity flowing, sure, but also a lot of heat from that friction, the brushes grinding on the commutator.
So you need cooling.
You need cooling. And the way these motors cool is by being open. They have vents, sometimes big slots, to let air flow through, convective cooling.
Ah, but there's the rub, those vents. They're like little mouths sucking in whatever's around.
Exactly. On a dirt track. That means dust, sand, grit. It's a direct path for contaminants right into the motor's guts.
And it makes its own mess too, right?
It does. That brush-on-commutator action constantly creates fine carbon dust inside the motor. And that dust is conductive.
Okay, so it's vulnerable by design. But then Tamiya goes and makes performance motors for off-road, like that super stock BZ. That's a 23-turn motor meant for racing.
And this is where the paradox kicks in hard.
Yeah.
To get that performance, the BZ needs even more cooling. So what did Tamiya do?
More vents.
Not just vents. The sources show they cut multiple huge slits right into the main motor can. Aggressive airflow design.
So they deliberately made it more open, more vulnerable.
Precisely. Maximum airflow for maximum power, which means maximum exposure to dirt. That's the deliberate design paradox we mentioned.
And the foam cover. That's the answer.
It's the necessary countermeasure. It allows that high airflow motor to actually survive the environment it was built for. It completes the package.
Okay, so let's talk about what happens when dirt does get in. Section 2. The contamination threat matrix.
Yeah, why is this debris such a big deal? Because these motors, especially the performance ones, are spinning incredibly fast. We're talking, what, 25,000 RPM, maybe more?
Easily.
So when you suck stuff in at that speed, it's not just sitting there, it's causing serious problems.
Yeah.
3 main types, really.
Okay, what's the first? I feel like I know this one. That gritty sound after a dusty run.
That's it, abrasive wear. Fine sand, silica, grit. It gets drawn in, trapped between the soft carbon brushes and the softer copper commutator segment.
It just grinds away.
Constantly, at thousands of RPM, it's like running sandpaper directly on the commutator. It just scours the surface, creates deep grooves, ruins the smooth contact.
Reduces power, kills efficiency, means you need a new commutator or motorway sooner. Okay, what's next?
Then there's a sneakier one, electrical shorting.
Ah, because the commutator segments are separate but close together.
Very close. Tiny gaps between them. Now, if conductive stuff gets in there, maybe metallic dust from the track, or even just that carbon dust we mentioned getting damp.
It bridges the gap.
Exactly. It can cause a short circuit between segments. Leads to erratic running, sudden power loss, maybe even fry your ESC if it's bad enough.
Yikes. Okay, abrasive wear, electrical shorting. What's the third? The big one.
Mechanical binding. This is the sudden stop, the catastrophic failure.
Oh yeah, the locked motor.
If something slightly larger gets sucked in a small pebble, maybe a tough piece of grass, a clump of mud, and it physically wedges between the spinning armature and the stationary can or magnets.
It just jams solid. Instantly.
Instantly. And the momentum, the power trying to get through, that's when you smell the magic smoke. Motor seizes, ESC burns out. Sometimes it even strips drivetrain gears from the shock.
So the foam cover. It's Tamiya's shield against all three of these.
It's their calculated defense. It's designed specifically to mitigate this whole threat matrix.
All right, let's finally get to the foam itself. Section 3. Filtration mechanics, the dry depth filter. How does this little sleeve actually work?
Okay, so first, what it isn't. It's not a perfect seal, obviously. Air has to get through.
Right, and it's not like a paper air filter in a real car.
No. And crucially, it's not a surface filter like, say, a fine mesh screen.
Right.
A mesh screen traps everything right on its outer surface.
Which sounds good, but clogs up fast.
Instantly, in heavy dirt, once it's clogged, airflow stops. Motor overheats. Game over.
So the Tamiya foam is different. How?
It's what's called an open cell depth filter. Imagine the foam not as a wall, but as a really complex 3D maze or lattice.
Okay.
It's full of interconnected tunnels and chambers. When air gets pulled towards the motor vents, it doesn't just hit a surface. It has to travel through this maze.
A tortuous path, as they say.
Exactly. And as the air twists and turns through the foam's entire volume, particles suspended in it lose momentum, bump into the foam structure, and get trapped deep inside, not just on the surface.
So it can hold way more dirt before it actually blocks the airflow.
That's the critical advantage, significantly higher dust-holding capacity. It keeps enough cooling air flowing for much, much longer than a simple screen would in really dirty conditions.
It's a pragmatic solution. Good enough filtration to stop the big damaging stuff.
Precisely. It's a pre-filter, really, designed to catch the sand, the grit, the small pebbles, the stuff that causes the abrasive wear and mechanical binding. It solves, let's say, 80% of the critical problem, which is catastrophic failure.
Okay, that makes sense. But here's something that always bugged me, and the sources confirm it. Tamiya never tells you to oil this foam.
Nope, no mention of it.
Why not? We oil foam air filters on nitro engines, on dirt bikes.
Yeah.
It makes them way better at catching fine dust. Wouldn't they be better here, too?
It's a great question, and it comes down to maintenance and, well, avoiding a different problem. Yes, oil traps fine dust better, but
There's always a but.
think about what happens. Oiled foam plus fine dust plus maybe a bit of moisture, a sticky, claggy mess.
No, it turns into sludge.
And that sludge can completely block the pores in the foam much more effectively and permanently than dry dust. It becomes a dense, non-breathable barrier.
So it could actually reduce airflow more severely in the long run and be harder to clean.
Exactly. Tamiya likely chose dry for simplicity, easier for the user to just blow it out or wash it, and to ensure more consistent, predictable airflow over time, even if it meant letting the finest dust particles through. They prioritized avoiding a total blockage over catching everything.
Okay, interesting trade-off, which leads us nicely into Section 4, the core engineering conflict, heat versus reliability.
Because using foam, even open cell foam, still means you're wrapping the motor in an insulator, right? Foam tracks air, cracked air insulate.
And the number one rule is don't cover the motor. Heat kills brushed motors. It weakens magnets, melts insulation.
Breaks down bearings, reduces efficiency.
Yeah.
It's the enemy. Yeah, Tamiya's literally telling you to put insulation on their hottest running motors. Seems crazy.
And this is probably why, like, serious racers back in the day often just chucked the foam, wasn't it?
Yeah.
Especially for indoor carpet or clay tracks. They wanted maximum cooling, period.
Absolutely. If you're running in a clean environment, the filtration isn't needed, and the slight insulating effect is a measurable performance disadvantage. Less heat means more power, longer runs.
So was Tamiya wrong then? Was the trade-off worth it only for bashers or really dirty tracks?
I don't think wrong is the right word. They were optimizing for reliability in the intended environment, messy off-road tracks. And the foam wasn't designed in isolation. It was part of a system approach to manage the risk.
How so? How did they mitigate the insulation problem?
Two key ways. First, think about those big vents on the Superstock VZ. What happens if one gets completely plugged solid with mud?
Instant overheating. Catastrophic.
Right. The foam cover, while slightly restricting overall flow, acts as a guard. It prevents those vents from being totally blocked by a single large object or clump of dirt.
So slightly reduced but guaranteed airflow is better than potentially zero airflow.
Vastly better. It ensures protected through-flow. And second, look closely at the motor. Where's the hottest part usually?
The end bell, where the brushes are.
Exactly. And notice that the finned aluminum end bell on motors like the BZ is mostly left exposed by the foam sleeve.
Clever. So the main heatsink area still gets direct airflow.
Correct. It provides a dedicated, uncovered surface to radiate heat away from the most critical zone. So Tamiya accepted a minor hit on peak cooling potential for a massive gain in preventing catastrophic failure from debris ingestion or total vent blockage in dirty conditions. Reliability trumped theoretical max power.
Okay, that makes a lot more sense as a system design.
Hmm.
But there's apparently another benefit, something less obvious. Section 5, the hidden benefit the motor as a debris cannon.
Yeah, this one is subtle, but I think it's really important, and it connects the motor directly to your drivetrain's health.
Drivetrain.
How? Think about the chassis these motors often went into. Tamiya buggies like, say, the DT Sioux, or even some early touring cars. They didn't always have fully sealed gearboxes.
Right, sometimes the pinion and spur gear are just out there,
Yeah.
maybe with a flimsy partial cover exposed.
Exactly. Now, picture that super stock BZ spinning away at 26,000 RPM on a dusty track. We said it needs massive airflow, right? It's sucking air in
Usually through the end belt.
and blasting it out through those big slits in the can. It's acting like a powerful little centrifugal fan.
Okay.
So, what's it blasting out? Not just air, it's blasting out any fine dust or grit that it did manage to suck in. It takes that abrasive debris, accelerates it, and shoots it out forcefully.
Wait a minute.
Yeah.
Where are those canned vents, usually pointing in a typical rear motor buggy layout?
Often. Directly at the exposed pinion and spur gear mesh.
No way. Are you saying the motor itself is actively sandblasting the gears?
That's the debris cannon effect. The high-performance vented motor becomes a primary source of high-velocity abrasive contamination for its own drivetrain. It's literally helping to shred the gears.
That is, wow. That's insidious. I never thought of that.
Mm.
Explains why spur gears used to get chewed up so fast, even with a cover on.
It's a major contributing factor. So the hidden benefit of the foam cover,
It stops the debris from getting into the motor in the first place.
which means the motor can't shoot it out at the gears, it effectively disarms the debris cannon. By protecting the motor's internals, it indirectly protects the entire gearbox. Huge bonus for longevity.
That's brilliant. Okay, so this foam cover sounds like a really smart, multifunctional piece of engineering for the brushed motor era, which brings us to Section 6, Market Evolution and Obsolescence. Why did they disappear? Why don't we see these on modern motors?
Well, the simple answer is the problem it solved largely went away. The foam cover is basically a technological fossil from the brushed era.
Made obsolete
The
by...
brushless revolution.
How did brushless motors change the game in this specific way?
Fundamentally, first, brushless motors don't have brushes or commutators. That eliminates the internal source of conductive carbon dust right there.
Okay, less internal mess.
Second, and more importantly, they're usually designed as sealed or semi-sealed units. They don't rely on massive vents and through flow for cooling nearly as much.
Why not? They still generate heat.
They do, but they're vastly more efficient. You know, a good brushed motor might be 75%, maybe 80% efficient if you're lucky. Brushless motors, they can easily be over 85%, some even pushing past 90%.
Meaning less energy wasted as heat?
A lot less. So their cooling requirements are just fundamentally lower. They don't need those huge vulnerable openings. A sealed can with external fins often does the job.
So a sealed design inherently protects the internals, making an external filter like the foam sleeve redundant.
Pretty much. Brushless technology solved the debris ingestion problem at the source by changing the motor's fundamental design and improving efficiency.
And if people do want extreme protection today,
Mm.
for bashing and sand dunes or whatever,
The market moved towards different solutions. Things like full chassis shrouds, those fabric or mesh covers that enclose almost the entire chassis. Companies like Dusty Motors make them.
right, those protect everything. Motor, ESC, receiver, gears.
Yeah, total protection. But it's a different approach. It's usually more expensive, and it can have a much bigger impact on overall heat management for all the electronics compared to just a simple foam sleeve on the motor.
So the Tamiya foam was a very specific, very targeted, low-cost solution for a very specific set of problems inherent to high-performance brushed motors in dirty environments.
Exactly. It really represents the peak of clever, pragmatic engineering within the limitations of that older technology.
Okay, so wrapping this up, what are the key takeaways for you, the listener? Maybe you've got an old Superstock BZ sitting around.
I think the main thing is don't dismiss that foam cover. Understand what it was designed to do. It's a dry depth pre-filter, yes, but it's also part of a calculated thermal trade-off, and it's protecting your drivetrain indirectly. It's doing multiple jobs.
So our advice, if you're running one of these motors, especially in anything other than pristine conditions, use the cover.
Definitely. Treat it as essential equipment for dirt, sand, loose gravel, even damp grass. The only time you'd really consider taking it off is for, like, Super clean indoor carpet racing where every tiny bit of cooling counts and there's zero debris.
And maintain it, right?
Yeah, clean it out periodically. Compressed air can work, or a gentle wash with mild soap and water, but, and this is critical, make absolutely sure it is bone dry before you put it back on the motor.
Because a wet filter is worse than no filter.
Much worse. Traps moisture right against the motor can. Bad idea. Let it air dry completely.
So the Tamiya foam cover, it's a great little case study, isn't it? Optimized not necessarily for the absolute fastest lap time on a clean test bench,
But for reliable performance and survival out there in the real messy world of the dirt track.
which leaves us with the final thought, maybe.
Yeah, it makes you think, doesn't it? When you're designing something, what's the true measure of good engineering? Is it pushing theoretical limits in ideal conditions, or is it creating something that reliably works when faced with the worst the real world can throw at it? When does functional reliability become more important than peak performance?
Something to ponder next time you're wrenching on your RC. That's all for this deep dive.